So welcome to lecture number 48 of the Statistical Thermodynamics course for engineers. So during the last lecture, if you recall, we calculated the oscillating dipole moment, which is given by this, okay? Which is given by this. So now that we have got an idea that what absorptions, we can now set the stage for the absorption spectroscopy. So we are going to do a little bit of rehash of what we already did in this PPT. So the sources are basically Bernard, which is spectra of atoms and molecules, the MS thesis of Professor S. Basu, and then there are web lectures and Hansen's Professor Ronald Hansen's lecture on tunable diode laser-based absorption spectroscopy. So some of these things we already did, if you recall. So there is no point in doing this. We know the electromagnetic spectrum already by heart right now. And we also have done the interaction of radiation with matter, which essentially translates to the interaction of radiation with matter. That means what is the energy difference and stuff like that. So we are already aware of things like, we have already done this earlier, that how interaction of radiation happens with matter by the two-level diagram that you see over here, that E1 and E0. So these parts are quite clear. And then we also did that when radiation, absorption of radiation occurs, the incident radiation density matches the exact frequency, and then we have calculated the different rate constants based on that. So as you can see, therefore, so these were the different rate constants. These were the different rates of population of the upper state and the lower state. And this is how we calculated, if you recall, how the spontaneous and the stimulated emission coefficients were related. So, for example, in an application like combustion, you have a lot of species: oxygen, nitrogen, oxygen, water vapor, and CO2. So absorption and emission of radiation, then we said, is given by the time-independent Schrodinger's wave equation. And then we solved for the dipole moment, and then we calculated the time-dependent coefficients. Forgive me about the symbols over here. So these are all covered in the previous classes. Okay, so we also know that what are the detuning frequencies and the resonant time scales. So spontaneous emission of photons, for example, we said, will break the coherence of excitation and reset the system to the ground state. Similarly, collisions can also reset the system. So collisions even can change the phase of the atomic or molecular wave function without disturbing the population density of each of the states. Okay. We also saw that the line shape in reality gets broadened by the damping factors, and it is given by the line shape function, which we saw. So for example, if you look at this plot over here, this shows the Lorentzian broadening and the Doppler broadening. So the Lorentzian profile is given by that equation, which you see the Lorentz profile. And then there is something called Doppler broadening, which happens because of the motion of the molecules. Lorentz profile comes from the pressure broadening. So together, the convolution of the Doppler and the Lorentzian line shape function gives you the final line shape, which is called the void profile. So this we also covered. So, and this is also covered, if you recall. So we also covered what we call the Beer law. Okay, so which takes into account that if there is an incident radiation from the left and it progressively gets absorbed within a medium, which has got a particular concentration of the species that absorbs the radiation, and if the radiation is kind of tuned to that particular wavelength, then we get what we call the absorption cross section, which is defined right over there. And we also saw that what will be the flux absorption as it passes through it. So this expression that you see over here is called basically the Beer's law. Okay, for absorption spectroscopy, basically Beer's law relates the attenuation in the intensity of incident light to the molar absorption coefficient and the concentration of the species N, whatever that species N is, whatever that species is. So many species actually have vibrational modes, for example, water. So in order to be IR active, the concerned molecule, we already said, either should have a change in the dipole moment or a permanent dipole or both. So water, for example, has a lot of vibrational bands, which are basically IR active. So that means the transition dipole moment for water is there. So the permanent dipole moment of water can be expanded in a Taylor series expansion about the internuclear separation distance. And that is exactly what you see over here, okay, where Q is basically the R minus RE, that's change from the equilibrium distance between the two nuclei. And mu E is the dipole moment when the bond is in equilibrium. So there is a permanent dipole, and then there is a fluctuating dipole because of the stretching of the bonds, right? So this can be axisymmetric stretch, as you can see over there, or it can be symmetric stretch, or it can be some kind of a bending of the molecule. So the real spectra of water, if you look at it, okay, it has absorption features for lines organized into bands, right, associated with a particular modes of vibration. These lines detected have very narrow features, but carefully observed at smaller time scales indicate that the lines have definite widths and characteristic shapes. So let me see. So as you can also, we noted that the line shape functions basically fall into two categories: homogeneous and inhomogeneous. So homogeneous line shape occurs when all molecules in the system have identical line shape functions. Inhomogeneous broadening or line shapes has when the inhomogeneous broadening occurs because of Maxwell-Boltzmann distribution of the molecular velocities. Now, pressure broadening, which we already did, is said to be homogeneous broadening. Okay, so pressure broadening is given by the normalized Lorentzian line shape, which you see over here. So, for example, quoting Bernard, okay, for a two-level system, the dipole moment oscillates at Bohr frequency except during a collision. So the Bernard, what he's give a nice explanation of collisional broadening is that if the collision is sufficiently strong, then the phase of the dipole moment is altered in a random manner by the encounter. The average time between two collisions, if it is T2, then the infinite sine wave is broken into pieces of average length of T2. So the effect of collision will be to convert an infinite narrow line shape to a line shape function of a finite width. So if you apply now the Fourier transform to the broken waveform, as you see over there in the figure, okay, into frequency components, it results in what we call a Lorentzian line shape, okay, with a full width at half maximum, given that's delta half as 1 over pi by T2, where T2 is the average time between two collisions. Understand? So there are collisions between the molecules, obviously. So as it collides, okay, the waveform is broken into these individual pieces, which has got an average time of T2, essentially. Okay, so this converts it from a narrow infinite, cosine wave, from an infinite cosine wave, it is broken into average pieces of length T2. Okay, now the Doppler, on the other hand, results in an inhomogeneous line shape. So this is the Lorentzian is applicable for all kinds of line shapes, right? Doppler broadening, on the other hand, results in what we call an inhomogeneous line shape function. So this transition basically has an homogeneous line shape centered around, say, V naught prime, and the inhomogeneous function, that is the Doppler broadening, is centered around V naught. So in the reference frame of the atom, it is a frequency of the electromagnetic wave that has been shifted with the atom at rest at the origin of the atomic coordinate system. Okay, so it is definitely given by the molecular velocity components V over here. For a gas along a given axis, it is given by the Maxwell-Boltzmann distribution, right? So the alteration in the frequency happens because of the molecular motion, because of the molecular velocity components. So the normalized Doppler line shape is given by this, which is a Gaussian distribution. As a matter of fact, it's pretty complicated to write. The full width at half maximum is given by this, and the total line shape function is given by what is given at the end. of the table, right? So the full width at half maximum is here, and the normalized Doppler line shape function is given like this. Okay, so if we now look at the profiles, so the Lorentz profile, if you see, is a Lorentzian in origin, and you can see that it is a little wide at the base, okay, and the Doppler is more narrower. So the convolution of these two profiles, which is called the void profile, is purely homogeneous or purely inhomogeneous line shapes at the limiting cases. For example, at certain pressures, the Lorentzian line shape may dominate, giving rise to a predominantly pressure broadened homogeneous profile, whereas Lorentzian line shape, which is given by the well-known Gaussian distribution, it's more sharply peaked. As you can see over here, it's more sharply peaked. Okay, it is more sharply peaked, okay, along the line center frequency, right? So the Lorentzian line shape has a clear dominance in the far wing region. So if you look at the wing of the distributions, so there the Lorentzian line shape clearly dominates over the Gaussian. Okay, so the understanding over here is that whenever you have an absorption spectroscopy, let me put it this way, whenever you have a radiation on a gas or any medium where the radiation is passing from this way to that way, right? So there is absorption of the radiation provided you have the frequency tuned to the molecular transitions concerned. Now, normally in this case, your absorption profiles should be very sharp. It should be like a Dirac delta function. But ideally, that is not the case. Why that happens? Because the molecules collide. And because of their collision that we saw, that the transition, which was nicely cycling, actually gets, it destroys the phase. It kind of resets the system, right? So that is what happens. And that actually enlarges the line shape, the frequency width. And that is exactly what we saw when it is a pressure broadening. That means that the concentration is high. We have too many molecules colliding with each other, and that is resetting the system. And because of this molecular velocity, we get further broadening because of the Doppler effect. So these are the two things that we should keep in mind. At the same time, if we look at the final form of the Beer-Lambert law, you will see that it actually, so F naught is the flux which is incident, which is coming out, and F naught is the incident flux. So these are the two components that you can measure. So when somebody is measuring by absorption spectroscopy, what do we normally do? You measure what is coming out and entering the medium, and then you measure what is coming out of the medium. So you know F and you know F naught. That means you know the intensity that is going in versus the intensity that is coming out, right? So the ratio of these two is given now by the exponential of what? The absorption coefficient, right? And the concentration. So if you know the absorption coefficient, you know the concentration, because the line, the total path length is also something that you know. That is that capital L. So more you increase the path, greater is this I over I naught ratio. As a result of that, more sensitive is your measurement. That means your error actually goes down a little bit, right? And it can be done for water, as we saw that there are various molecular species which has got vibrational modes, and water being one of them, which has got a permanent and a fluctuating dipole. And that is what leads to the large number of IR active bands. So IR spectroscopy is regularly used for water. So in this case, we use something which is called a high trend database. So high trend database is a compilation of spectroscopic parameters, right? Where a variety of molecular computer codes are used to predict and simulate transmission and emission of light in the atmosphere. So database is a long-running project started by the Air Force Cambridge Research Laboratories in the late 1960s, right? So the high trend database actually is composed of over 1 million spectral lines of 36 different molecules. And if you look at it now over here, if you look at the sample table, you will see several types of air broadened half wave, self broadened half wave, and all these parameters are listed. So these provides the unique opportunity for us, to use in computer simulation and theoretically predict what will be the, the spectral signatures. So when you do actually Beer-Lambert law, when you look at the, say, for example, the water, you see this many number of transitions at different temperatures. So as you can see, now if you pass this through a sample, you can measure the partial pressure of the species, whose partial pressure is nothing but the concentration of the species. That can be uniquely measured. And you can simulate the line shapes at different temperatures and concentrations. For water vapor, for example, this is water vapor, done at different partial pressures. So 0.19 atmosphere to 0.45 atmosphere. You see the absorption coefficient versus the wave number. You see that this is the line shape that you get. This is done by simulating it by using an actual void profile. So the simulation results for the cell temperature, for say water at whatever temperature, 80 degrees Celsius, for different partial pressures. And in this particular wave number space, we have 4 major transitions. So here what we see, the half width increases as we increase the partial pressure of water, because we increase the collisional broadening, right? The maximum intensity decreases with increase in partial pressure. The extent of variation of both peak intensity and half width with partial pressure is very high. So both of these parameters are sensitive to partial pressure. That is what we can say over here. So this is at different temperatures, for example, from 60 to 80 degrees Celsius. So here you can see that if we see the change in the temperature, the variation of line shapes at different temperatures. Okay, so this is what you get. So here the half width doesn't change by that much, right? Okay, but well, it changes, but it doesn't change by that much. So the variation of half width with partial pressure is about 38%, not so much with respect to temperature. Okay, so how do you measure it experimentally? Okay, so experimentally you measure it by what we call a direct absorption or wavelength modulation spectroscopy. So what happens is that you have a laser, typically a laser, where you actually have a ramp function, this is the injection current tuning of the laser. And then what you do is that you measure, if it is direct absorption, you measure what is going in, which is I naught, and what is coming out, which is IT over here. And then you see that there is, if you measure the I, you will see a blip. Okay, so that blip, if you kind of do the measurements, if you kind of do the processing, it will give you this kind of a distribution, which is basically nothing but absorption, direct absorption line shape function. Okay, so this is done what we call using a TDL, or tunable diode laser based absorption spectroscopy. There are other variations of it, which is like wavelength modulation spectroscopy, which is kind of not something that we are going to do in this particular lecture. So it is usually done by a frequency modulated diode laser. Okay, so the diode laser, and if you do not know what a diode laser is, these are semiconductor devices with PN junctions. So normally the laser diodes are edge emitters. So the difference between an LED and a diode lies in the fact that LEDs only emit incoherent radiation. Laser diodes emit coherent radiation when they are operated about a certain threshold. So, and you can read about this phenomena, okay, and distributed feedback diode lasers are used for uses corrugated semiconductor substrates. So these are all a little bit of optics, which you don't necessarily need to know. Okay, so we are going to skip those, but these lasers are easily available in the UV and the far IR. Near IR lasers are very compact and rugged and fiber coupled, as you can see over here. So they can be rapidly tuned over several wave numbers. That's why we get that range over which we want to measure a transition, and by changing the injection current or the laser temperature. So that provides with a framework. Now, to detect the radiation, you use either photodiode or photovoltaic detectors. So photodiode is a semiconductor device that generates voltage or current when light is incident on it. Like photoconductors, they have a minimum photon energy associated with the band gap energy of the semiconductor. So there are variations of photodiodes, which once again is something that you can read. So this is how this is done. The laser current is modulated by a ramp function. Scan range is typically about 0.4 nanometers, so very short. The laser wavelength is calibrated usually using a ring interferometer. That what is the absolute wavelength at which it starts. Multiple scans are therefore averaged. So this is very fast. You can do it very fast. So what happens is that you have a reference signal. So you basically take the output of the laser diode, split it into two, 50-50 almost. One, you pass it through the test cell, which contains the species that you want to measure, and the other is passed through a photodiode, which measures that what is I naught basically. So once it comes out through the test cell, then you use another photodetector or photodiode to measure I. So and then you plot one on the top of the other, and then you take the ratio. Output is that signal by reference. So I over I naught. And basically you get this kind of a line shape that you see over here. Okay. So this now tells you that once you plot this spectrum, this is now represented by not one transition, but several transitions. In this case, there are about 4 transitions that you can do. So this actually, by measuring the change in this line shape, you can measure what is the partial pressure and what is the temperature. So how do you, as you already saw, that these profiles actually change quite a bit. If you look at it here, quite a bit with respect to concentration. So if you increase the concentration, the half width increases. So basically you are measuring this line shape using that I over I naught ratio. So this I over I naught ratio, using this, you are precisely measuring that. Now you already know, if you have pre-calibrated this, you already know for known concentration what is the half width, and then you use that over here to calculate the any unknown concentration that you might encounter. Okay. So this is the line of sight based direct absorption. So it has to come out. So it is averaged over the distance L. Remember the distance L, that is over the distance over which we have kind of, averaged it out, right? Okay. So and it is the logarithmic ratio. So you can see the 2 different measurements, for example, they look very identical. The base is sometimes shifted, but that is not a problem. You can just move it up and down. So that is not an issue at all. Okay, so they look, although the measurements at the same condition of partial pressure and temperature look identical, they can have different backgrounds. So this difference in variation in background is can be attributed to something called an Etalon effect. So Etalon fringes and periodic ripples can appear. So these are all things that you need to take care when you do a measurement. So one is theory and one is when you actually execute it. So the execution always involves unforeseen effects, like for example, the Etalon fringes, right? All these things appear and you have to kind of, take care of that. Okay, so wavelength modulation we are going to avoid. So that is not within the scope. So near IR and visible spectroscopy, absorption-based sensors therefore have highest sensitivity and selectivity because of that extremely narrow spectral source that we use. So you can tune the wavelength to whatever transition features that you want, and that from that you can isolate what will be the concentrations or the temperature. So most applications relevant to gas dynamic and combustion flows are based on absorption by low molecular weight molecules with well-resolved absorption transitions. Okay. So with the exception of visible transitions of O2 and NO2, the absorption measurements are performed on overtone and combination of vibrational absorption bands. So typical line strengths of these absorptions are between 10 to 20 centimeter per molecule, right? So the number of molecules of interest in combustion flows possess transitions near this 1.55 micron windows. So there are a lot of these measurements are quite easily available. The small species, you can see they have discrete rotational transitions in the vibrational bands. Larger molecules have blended features. So all these are absorbents of NO, CO, CO2, water, and that last one is N-totocane, right? So you can also have, a complete sensor architecture in which you can have different lasers which are coupled, fused, and then so the beam that comes out of it has got combination of all these wavelengths, and then it is passed through your experimental setup, which is shown right over here, and then you detect the signal, and then you again you can measure all species at one particular go, multiple species at one particular go. Okay, so the laser itself is like a communication style fiber pigtail package, so this is not a problem. And this is something that you get something like this from laser 1, laser 2, laser 3. CH4 is methane, CO2 and water. Okay, so these kind of measurements can be performed, and then there can be also other kind of measurements like, you know, flame and combustion emission measurements are also done. Okay, so this is used in high-speed flows, diffusion, premix flames, spray environment, reacting systems like fuel cell, you know, flow through porous media, also used as trace pollutant measurements, detection of explosives in the airports. So even used in combustion instabilities, it is extensively used in atmospheric sciences. So all these things are something that is done through absorption spectroscopy, which is rather easy. So we saw how an Einstein, two-level system, how we can do the math, and we can show exactly what will be the line shape functions, what are the forms of the line shape functions, right? Why the line shape functions actually exist, and how the line shape functions actually respond to partial pressure and temperature. So with this, I think we finish the spectroscopy part of this course. There will be tutorials that will be there. There will be also a small tutorial on laser-induced fluorescence, which will be the concluding part of this particular lecture. So yeah, so this basically concludes some of the lecture portions of this particular statistical thermodynamic course. Thank you so much.